Okay, inverse of a function. The first thing we're going to do is we're going to make sure that it's understood how to solve for x. So if you're given f of x equals 3x minus 2, I'm going to write that as y equals 3x minus 2. I'm going to go ahead and get x by itself by adding 2. So I have y plus 2 equals 3x. And then divide by 3. So x is equal to y plus 2 over 3. Can also be written as 1/3. There's a 1 in front of that y. Y plus 2/3. We've now solved for x. Okay. So kind of using that information, either one of these would be fine. We're going to go ahead and look at inverse functions. Any pair of functions that undo each other are called inverse functions. An inverse function can be obtained by interchanging the placement of x and y. So the first thing I'm going to do, I've already done 3 of the original function and finding the inverse, right? I can take and rewrite it as y equals 3x minus 2, add that to y plus 2 equals 3x, divide by 3, y plus 2 over 3 equals x, and we know that is still the same as 1/3 plus, or 1/3 x plus 2/3. There is the inverse, or 1/3 y, excuse me, plus 2/3 equals x. Now, when we want to write it as the inverse, we interchange x and y, especially if we're going to graph it here. So we're going to write it as, rather than x equals that 1/3 y plus 2/3, we're going to go ahead and interchange these. So these two are going to switch positions. We're going to go y is equal to 1/3 x plus 2/3. Okay, that is our inverse function. That function right there would undo that function. Okay, so filling out a table of value and graphing these real quick. I'm going to go ahead and switch colors for this function here. If I'm finding f of -2, I'm not going to show this for everything, but I'm going to assume we know how to substitute things in. Okay, so that's 3 times -2 is -6 minus 2 is -8. f of -1, 3 times -1, -3 minus 2 is -5. f of 0 is, oops, not -3, but -2, and 1 and 4. So if I'm plotting this function here, my original function of f, I can go ahead and put those points in there. So -2, -8 actually won't fit on our graph. We're going by ones, 1, 2, 3, 4, 5, 6, 7. And we'll go ahead and add a place there, -8. Okay, -1, -5, 1, 2, 3, 4, and 5. Okay, and 0, -2, 1, 1. All right, and 2, 4. Almost missed that point there. Okay, and then I go ahead and I'll draw my line there. All right, there's the graph of f. Okay, now to find this function, and by the way, we can write y equals 1/3 x plus 2/3. We can change that to g of x if we want, is equal to 1/3 x plus 2/3. So now it's in function notation. Okay, but anyway, really what's happening is you're just interchanging your x and y's. What was x becomes y, just like we did here. We interchanged our x and y's. We do the same thing in our tables. Okay, so all my x's are now y's. -2, -1, 0, 1, and 2. And all my y's are now x's. -8, -5, -2, 1, and 4. So I have -8, -2, which, by the way, -8, 1, 2, 3, 4, 5, 6, 7, -8, right? It doesn't quite fit, so we'll add it there. This was the -5, okay? -5, -1, 1, 2, 3, 4, and 5, and -1. And -2, 0. And 1, 2, okay, and 1, 1, and 4, 2. 1, 2, 3, 4, 1, 2. Okay, and got our line here. That is now G. Okay, and you'll notice that the domain and range for each of these f and g are both all real numbers. They continue off on the x value. They continue to the right forever and to the left for domain. And range, they continue up and down forever. So both all real numbers there. So I'm going to go ahead and put that in. That hasn't changed. But you also notice here the graph of an inverse function. If I were to draw this line in right here, that line is the line y equals x. And this point right here, we know is the ordered pair 4, 2, but that is actually a reflection of that point, which is the ordered pair 2, 4. Okay, when x and y switch, when you graph those, the graph of an inverse is a reflection over the line y equals x, which makes sense because we've made our y values equal our x values and our x equal our y's. Okay, so it's just a reflection. So when you're looking at a graph of these, you want to know if they're inverses. See if they're reflections of each other. See if the x's and y's just transpose there. Okay, you can interchange those. All right. Well, let's evaluate or go through this a little more here. The inverse, find the inverse of f of x equals -1/4 x plus 3, then graph the function and its inverse. So the first method when doing this is you could solve for x first, if you want. And that's kind of what we've been doing. Oops. Solve for x, that's kind of method 1 here, or what I'm calling method 1. Okay, so I could take and change f of x to y, y equals -1/4 x plus 3. I can solve for x, so subtract 3. Oops, -1/4 x. Okay, multiply, excuse me there, and clean that up there. Multiply both sides by -4, so I get -4 times y minus 3 is equal to x. And then, after I do that, I can switch x and y. All right, which if I do that, I now have, excuse me, I now have -4 times x minus 3 is equal to y. Okay, and I guess if I'm going to graph this, I might as well, do this. So I get -4x plus 12 equals y. And really, I shouldn't be calling it y because this is y here and this was f. So really, let's call this g of x. Okay, so now it's not the same as what I had before. Okay, and so my function is g of x equals -4x plus 12. That is the inverse. Okay, so that's kind of method 1. Method 2, start by switching x and y. Okay, so if you want to, on method 2, you could switch x and y first. Let's go ahead and kind of separate the, oops, didn't mean to do that. Separate these out a bit. Okay, so I could start by having y equals -1/4 x plus 3. And then x and y. Okay, so I'll just kind of swap these two. So I get x equals -1/4 y plus 3. Subtract 3. Multiply by -4. And then simplify it. I get -4x plus 12 equals y. Okay, and then we'd call it g, right? So we'd say g of x is equal to -4x plus 12. So really you do the same thing. It just depends when you want to switch x and y and which textbook you're using. Okay, what I am going to do though, I am going to go ahead and graph the original function here. Okay, f. So y-intercept is 3, 1, 2, 3. We have a slope of -1/4, so down 1 and over 4, 1, 2, 3, and 4. And we see the trend 1, 2, 3, and 4. Okay. Oops. Got to go up one there. Okay. And we have our graph here. If I can Sorry about that. And I really should find my straight edge, but for some reason I cannot. All right. Let's see. Oh, you know what? I just found one, so it'll make it look a little better there. Okay, hopefully. There we go. Okay, and so that is F. Now you'll notice if I use the y-intercept for my inverse, the y-intercept is 12. And the problem with that is this graph doesn't go up to 12 and it didn't change my scale. But the other thing I know, remember, I could just switch my x and y. So this coordinate right here is at 4, 2. So I could go to x is 2 and y is 4. And that is my new coordinate there. Okay, so and this coordinate, which is at 0, 3, or 0, 3, would be at 3, 0. Okay, so this 0, 3 is now at 3, 0. This 4, 2 at 2, 4. Okay, 1, 2, 3, and 4. So negative 4, positive 4 is going to be at positive 4 and negative 4. Okay, so those two switch. And by doing that, you'll notice, let's see, I got my straight line again. I got it. That is G, and note that G should be a reflection over the line. See if I could draw y equals x here. Be a reflection over the line y equals x, and yeah, they are. All right, so very good. Well, inverses of nonlinear functions. So one other thing we have to consider is when we're finding the inverse of a nonlinear function, it's sometimes necessary to restrict the domain. Otherwise, the inverse isn't actually a function. So if you'll take a look at your original function, y equal, or f of x equals x squared, and then the inverse is y equals the root of x, okay? You'll notice that the inverse isn't a function. It doesn't pass, remember our vertical lines, it doesn't pass the vertical line test. Remember, if a vertical line hits a graph in more than one spot, it's not a function. Whereas the original did pass the vertical line test, right? We draw in a bunch of vertical lines, it does pass it. So this is a function. Okay, not a function. Okay, f of x equals the cubed, or x cubed. Well, you know, it passes the vertical line test. This is a function. Well, if it's inverse, the cubed root also passes the vertical line test. So it is also a function. So really, the ones you're very concerned about are your even roots. Okay? Even roots you need to be concerned about. May not be functions. Okay? I know that that's really fairly messy there, but that's supposed to say functions. All right. So one thing we can do is what's called a horizontal line test. If you're not sure what the inverse will look like when graphing it, what you could do is you could look at your original function and you can do what's called a horizontal line test. The horizontal line test takes your original function and you draw horizontal lines. If your original function passes a horizontal line test, then the inverse will be a function. Notice this one doesn't pass the horizontal line test. Does not pass the horizontal line test. Therefore, the inverse is not a function. Whereas this graph does. It does pass the horizontal line test, which means passes horizontal line test. So the inverse is a function. All right. So that's one way to determine if it's a function. So if I'm going to look at some graphs here, so first find the inverse of the function, and the inverse of the function f of x equals x squared when x is greater than or equal to 0. So notice I'm restricting the domain this time, then graph the function. Okay, so I'm going to restrict the domain. I'm going to go ahead and say, okay, well actually, let's graph that function first. So f of x equals x squared when x is greater than 0. So that is 4. Okay, that is that graph right there. Notice the quadratic would usually go up over here as well, right? However, we only want when x is greater than or equal to 0, so on this side. Therefore, I kind of ignore this chunk of it over here. All right, so that's the graph of f. Now the inverse of f, let's go ahead and take that and find g. So I'm going to rewrite it as y equals x squared. I'm going to go ahead and take the square root of both sides. So I get the square root of y is equal to x. And notice it's plus minus. Okay, and then I'm going to switch them. So plus minus the square root of x is equal to g of x. Okay, or y, which I'm going to call g of x. So I'll rewrite this as g of x is equal to the plus minus root of x. And what that does then, when I'm looking at it, usually the plus minus, so here's the positive root of x, right? It's at 0, 0, 1, 1, and 4, 2. Okay? And so that is this branch. The negative root of x goes over this way, right? And so that would be this branch. Well, when I switched the graph, when I switched the x and y values, my restriction on my domain now becomes a restriction on my range. Okay, so domain and range also interchange. Okay, so we should say restrictions. Okay, so the restrictions on our domain and range also interchange. So therefore, y has to be greater than or equal to 0. That means I get rid of this bottom chunk here. And note also, like if I were to look at the reflection here, here's my reflection over the line y equals x. This point right here that was at 2, 4 is now at 4, 2. Okay, so those are reflections. This one's on the line and this one's on the line. Okay, so when the domain of a function is restricted, the same restriction is posed on the range of the inverse, and that's what's happening right here. Okay, so let's go ahead and take a look at another one. Find the inverse of f of x equals x squared plus 2 is the inverse of function. Well, I can actually answer the last question, is the inverse of function, by thinking of what this graph looks like. This is f of x equals 4x squared plus 2. This is a quadratic. Its picture looks like this. There's no restriction on it. Therefore, what I should be asking myself is, does it pass the horizontal line test? And the answer is, okay, the original function does not pass the horizontal line test, so the inverse is not a function. All right, And then if I want to go ahead and find the inverse, that's the other way to think about it. I can change that to y equals 4x squared plus 2. Subtract 2, so I get y minus 2 equals 4x squared. Divide by 4, y minus 2 over 4 equals x squared. And then take the root. When I impose the root, I've got to put that plus minus. Y minus 2 over 4 equals x. And let's go ahead and simplify this. This is plus minus the root of y minus 2 over the root of 4 equals x. Oops, not equals 4. Which becomes plus minus the root of y minus 2 over 2 equals x. Interchange or switch x and y to get y equals the square root of x minus 2 over 2, which is the same thing we're going to call g of x now. And should have that plus minus. That's kind of a big deal there. Plus minus x minus 2 over 2. There's the inverse. Okay, and if you know square root functions, this function would open sideways. Therefore, it wouldn't pass the vertical line test, so definitely not a function. All right, let's go ahead and take a look at this next one here. The inverse of f of x equals 2 times root x plus 4 is the inverse of function. Well, it's a square root function. It's not one that we use as much. So what I'm going to go ahead and do is I'm going to find its inverse first. Okay, so y is equal to 2 root x times root x plus 4. I'm going to go ahead and divide by 2, so y over 2, not minus 2, y over 2 is equal to the root of x plus 4. I'm going to go ahead and square both sides, so I get y squared over 4. Okay, when I square y and 2, it's equal to the root, that gets rid of the root, so I get x plus 4. I'm going to rewrite this as 1 over 4. Dividing by 4 is the same thing as multiplying by 1/4. Y squared, x plus 4, and then subtract 4. So I get 1/4 of y squared minus 4 is equal to x. I'll interchange them, the x and y, so I get 1/4 x squared minus 4, and we're going to call that g of x now. There's my inverse. So I'll rewrite it as kind of in our normal format there. And I know that this is a quadratic, right? This is quadratic. Therefore, it is a function. I know all quadratics, unless there's a restriction on their domain, are parabolic, and that is a function. So the inverse is a function. So you could test with the horizontal line test, or you can figure the inverse and then use or think through what type of graph it is. Okay. All right. One last thing is verifying functions are inverses. So to determine if a function is if functions are inverses, first evaluate the function for a specific input, then evaluate the inverse using the output obtained. If the output of the inverse is the same as the specific input you originally used, then the functions are inverses of each other. Now, just so you know, that sounds like a lot of talking in circles, but really, I'm going to take it step by step. To determine if the functions are inverses, okay, very good, evaluate a function for a specific input. So in other words, put a number in. So I'm just going to pick like 2. I'm going to say, okay, f of 2 is equal to 2 times 2 plus 7. Okay, which gives me 4 plus 7 or 11. All right. Then evaluate, you know what, let's go ahead and switch up colors here. Oops, didn't mean to do, whoa. Well, let me pause. Hello, I'm back. All right, let's go ahead and switch up colors now. Okay, we're in red. All right, perfect. Okay, then evaluate the inverse using the output obtained. Well, here's the output I obtained. It's 11. So I'm going to take the inverse, or what I think might be the inverse, and use that output in it. Okay, well, 11 minus 7 over 2. Well, that gives me 4 over 2, which equals 2. Okay. If the, let me switch up colors again. If the output of the inverse is the same as the specific input originally used, so here's my output. If it's the same as the input originally used, which it is, then the functions are inverses. F and G are inverses. Okay? Hey, the other way to do this, and let me go ahead and switch this up one more time here. The other way to do this is to see if f of g of x is equal to g of f of x. Now I know that looks a little confusing, but really all this means is if I take my function f, 2x plus 7, and I substitute in for x my function g, which would be 2 times, well, here's g, x minus 7 over 2 plus 7. Okay, and simplify that. Okay, well, I'm going to keep working down here. Notice 2 and multiplying by 2 and dividing by 2, those two things cancel. Left with x minus 7 plus 7, which is just x. Okay. If that equals g of f of x, now that means I'm taking my function g, x minus 7 over 2, and substituting in f for x. Well, f is 2x plus 7. So I now have 2x plus 7 minus 7 over 2, which is 2x, 7 minus 7 is 0, over 2, which is x. If those two things are equal, or if f of g of x equals g of f of x, which equals x, if that is true, then they are functions. Okay? F and g, I'm sorry, they are not just functions, they are inverses. Then they are inverses. I misspoke there. So if f of g of x and g of f of x equal x, then f and g are inverses of each other. Okay, well, that's all I got for you. Good lucky.